not easy. What's it coming in on Monday? Monday? Oh, come on. Monday. Oh, Monday. Next Tuesday.
Might be here Tuesday, just not Monday.
What will you be here for?
Getting the screen, no?
We see you, but we can't see your pad. There it is. Never mind.
Okay.
We're good.
Life is
Alright, good. Alright, so what was the last problem that we did last time?
Number 11 is the integral sine squared.
Alright, so now I was just kind of talking about it, right? I didn't finish the problem. So let me just kind of start over. I didn't bring the paper. So the integral, and that was number 11. Okay. So we had integral, and that was sine squared of x dx. So as I was saying, if we look at the problem, we may see the composition, which is sine of x squared. But if you go with the substitution here as u equals sine of x, it will not help, because then you will have that cosine of x on the bottom. So that's not the right substitution to go with. Here it's a more complicated problem, and I'm just showing you just to see the difference, like what kind of problems we have. But overall, the way to deal with this, let's say with this limited knowledge that we have right now, is to actually use the identity. So we have to go with 1 minus cosine, and what did I put? Cosine of what? 2x over 2 dx. So that's what we have. We'll go with this substitution and identity. So now we're going to split this as 1 over 2 minus, well, we actually can factor out, right? 1 over 2, yes, no? Or what did I do last time? I keep it like that?
Yeah.
Okay, so let's keep it again. Cosine of 2x over 2 dx. And then either you factor out 1 over 2 completely outside, or deal with each piece separately. Did I factor or just kept? Did I actually split it or not?
You split it without factor.
Okay, without factoring. So we have 1 over 2 dx minus integral the sine of 2x over 2 dx. Probably be easier if I factor out, but since I didn't do it, let's keep it this way. So this one shouldn't be that complicated to work with, right? This will be just what? Now, but what else did I do anything else? Because I didn't bring the paper. Like, what did I do after this? Okay, as far as you go. So this is what we do now. Now we have two integrals, and I have to deal with each of them separately. And normally, when we have two integrals, and this one's easy to find, this tiny bit more complicated, so normally we just name them. For example, like the first one, I call I sub 1, so integral 1. And the second one I'll call integral 2. And the reason I do this, because the second one, specifically the second, I cannot get right away, let's say. Okay? So I have to work with them separately. So I'm going to pause for a second here, and I will find what the first integral is, and that's easy. So for example, my I sub 1 is actually integral of 1 over 2 dx. And this will be just what? What's the antiderivative of 1 over 2? So 1 over 2x, right? Now, put plus c, but you have to understand, at the end, we're just going to put plus c and nothing else. So don't worry about if you put c or c sub 1. So that's the first one. Now, the second integral, it's integral cosine of 2x over 2 dx. Here you can pull out then 1 over 2. Now, this one is the composition, okay? And we'll use very simple substitution. So what is the substitution here? 2x, right. Just 2x, because if I have cosine of u, then it's easy to find antiderivative, okay? So it's 2x. So du over dx will be 2. And then we have dx equals du over 2. So if we put this back, we get 1 over 2 integral of cosine of u times by du over 2. So the next step, I'm going to take this 1 over 2 from inside, outside, so I'll get 1 over 4, right? If you take this outside. So you get 1 over 4, and you have, and then what is antiderivative of cosine? We get negative sign or positive sign. So what do you think?
Sine, positive.
Well, let's think about sine, right? So if I put, for example, sine of u, right? What's the derivative of sine? Just cosine, right? If I would have sine of u and you're looking for antiderivative, in that case you get negative, right? So careful. And I'll put plus c. Again, remember, right now it just doesn't make any difference. It's just a constant. Then go back to your substitution. So you get 1 over 4 sine of 2x and plus c. So you found them each separately. Now we just have to go back and put them right here. Okay? And don't worry about, don't put plus c. We'll have just one c at the end. So the first one is 1 over 2x. Okay, I have to move it down so you can see what I'm writing. Plus, and then I have 1 over 4 sine of 2x, and that will be just that 1c sitting at the end. So that will be the final answer here. So the difficulty is not actually here to find like these two integrals. Difficulty is to know that you have to use identity. Okay? And normally, something like this I don't put because it's not directly related to substitution method. There's two steps, using identity and then using substitution. So something more easier you will have on exam, but I'm not saying you're going to have 1 over 2x, okay, or dx, whatever, integral like this. So let's do quickly one more and then we'll move to the next section. But please, again, I know you have lots of things to do, but you have to practice. It's not a good idea to wait for the last moment not to finish and still not having enough time, so never coming back and reviewing those problems. And coming to the test without practice is just basically a big disaster. It's just a waste of time. So let's take a look at one more, and this will be number 12, right? So, integral of cotangent of x times by a natural log of sine of x dx. Okay, so let's take a look at something different. Now, and by the way, if you go to nodes, I actually have 5.53 nodes. Now, we're not going to do this, but some of them right now, like this one, I'm picking from the third lesson, okay? But we don't have time to have the third lesson. If you need to see more complicated problems, then you can go and look at them, but those are not on the exam. I just purposely showed how difficult sometimes substitution is if you only know just substitution method. If in Calc 2, when you have more knowledge, more methods, the sum integrals that right now looks big and enormous, then will be much smaller and easier to work with. Okay, so you can look. Well, let's take a look at this one. We definitely see the composition, right? And can you tell me, just kind of guess right now, what do you think the substitution is?
Sine of x.
So it looks like sine of x, but actually that's the wrong substitution. Because the right substitution is natural log of sine of x. But remember what I told you again? you try it, and it's not going to work. Then what? Come back and rethink the substitution. Okay, so if you set sine of x and you try it and it doesn't work, well, it doesn't mean the problem is wrong, right? It's just the wrong substitution. So here, what we have as a substitution, and you will see why, okay, in the moment, the substitution will be natural log of sine of x, not just sine of x. So then, what we have du over dx, and remember, natural log of sine of x is a composition. So, what do we get? Well, we get 1 over what? Sine of x, right? 1 over sine of x as for a log, outside function. And inside will be what? Cosine of x. And this is what? This will be cotangent. So question, do you understand why we use this substitution? Because if you go to dx, what do we have? We have du divided by what? Cotangent of x, right? And when we substitute, we get cotangent of x times by u. That's our natural log of sine of x. And then we have du over cotangent of x. If you would choose, for example, the previous one, like u equals sine of x, you will have like dead end. You will not do anything with this. So these will be canceled. So now we have very simple integral. And we have u squared over 2 plus c. And then we substitute. We'll put this. Now we'll be careful here. I would put it like this. That's more safer to put it in this form, just substitution, over 2 plus c. And this will be the answer. Okay? And again, you can check if it's right. Overall, these functions are not difficult, not complicated if you look. It's not that difficult to take derivative of this function and see if you can get this. Not too complicated, as long as we know how to differentiate. So, just a couple extra examples from previous section 5.5. So, we're done with chapter 5. Now, theoretically, let's put it this way. Theoretically, when we're finished with chapter 5, then you should know how to find integrals. And again, when I say integrals, what? Fitting into these concepts. Not everything, but simple integrals and also integration by substitution. So you should know. Now, obviously, this is just an assumption, right? A good wish, but it comes with the practice. So what we're going to do right now we're going to chapter 6. This is the last chapter that you will see. Yes, it will be your Calc 1. Now, in Calc 1, even in chapter 6, I'm still not doing every single section. There's one that I will not do, and that's section 6.4. I don't have a book. I think we call it work. Okay, section we call it work. Well, it's more from physics, okay? And normally why I'm not touching this because I don't know your experience with physics. And normally, you know, when I get students here, I don't know about high school, it depends. Okay, guys, any of you taking physics? Yes, no? Minako?
No.
No.
No, okay, so I have one student. Did you take? I think you took it last semester, right?
Yeah.
Okay. You had it for the whole year? Did you learn something?
A little bit.
Okay.
Not sure how much.
I should ask that question, right? But anyway, and so it's from physics, a section from physics, and we're talking about work. And again, you see, not all of you have seen this. And then when I do easy problems, it kind of doesn't make sense. But I really, with work concept, you want to do more complicated problems. And then it's like, what just happened? Many students don't have experience with physics. So I'm not touching that subject. But everything else goes in. So we're almost at the end. So what's left for us? Let's kind of briefly say what's left. Today we're going to talk about area between curves. Okay? That's one thing. And the rest, we'll talk about volumes. Now, the integrals for volumes or areas are not that big, not complicated as integral itself. or what's so difficult or complicated or confusing is to set up the integral. So it's not going to be just like find integral. No, you will see today it's going to say find area between the curves. And you have to set up the integral. You have to put it together. And if you make one mistake, the whole thing is wrong. So this is probably the most difficult part. Not integral as itself. They're very simple integrals. So let's get a look at a couple of problems from 6.1. And tomorrow we'll start talking about 6.2, maybe still one or two from 6.1. We'll see how it goes. But one thing, again, what my concern is, as Minika, is for you, because you don't have school on Monday and Tuesday. And we don't have school on Wednesday, Thursday, Friday. Well, actually, I'll be here on Wednesday, but you students here, you don't have school on Wednesday, Thursday, Friday. So the reason I say my concern, because I have to start teaching the section 6.2 and 3, and those are volumes. So I don't know, I know Mr. Hinckley said that he will be recording them. I don't know if you're actually watching those, I have no idea. So I'll post the notes, but again, notes do not talk. So you really have to read the book, really have to understand. Or I'm on Monday and Tuesday, okay? That's a choice. That's the problem, having different schedules. So let's continue, and I really don't know what to do with this. So we have areas between curves. So remember before I told you, chapter 5, the beginning was what? Area under the curve, right? And that was the curve and x-axis. And it doesn't make a difference if that curve is on the bottom, right? It's still curve and x-axis. And for the areas between the curves, we could have answer as positive or negative, right? It depends where the curve is, or the area, right? If it's above x-axis or below. Now for this concept, areas between the curves, the answer is always positive. Always positive. So it's just kind of in case you will get something negative here, that means you did something wrong. And normally, the wrong part is just switching the function. So that's not that difficult to fix. But let's take a look and look at a little concept here. So let's say we have a picture like this. So let's say I have interval A and B. And we have a curve, y equals f of x. And then somewhere over here we'll have y equals g of x and second curve. And we'd like to have area between the curves, and you see where that is, right? It's literally what? Between the curves. So here is the area that we have to find. That's the area. So the question is, okay, I see the picture, I know what that between is, but how do I set up the integral? So what do you think? What did you do?
Set an integral for the bigger one, subtract that, the integral for the small.
Alright, well technically what that means. First you find integral of f of x, right? That means what? Area from f of x down to what? X-axis, right? From here to way down. And then you find the second integral, which is area for what? G of x, and it's only this piece. And when you subtract, you get this, right? So technically, we're coming down to what? F of x minus what? G of x dx, right? Now, it's always, and I'm going to go a half. We don't have that much time, but it's always the top curve minus what? The bottom curve. If you will flip them, for example, if you say G of x minus f of x, then what? You get negative area. So that's what I was saying. Normally, that's what we have as a problem, is flipping the functions. Now, so that's what we have.
It doesn't seem too complicated, right? I feel like look at much more than all.
Yeah, it's not complicated overall, but let's talk. We'll see, okay? Just wait. So, if we look at this, let's take a look at the second maybe possible outcome. So let's say you have still from A to B. Here is your y equals f of x, but g of x, let's say, is right here. So where is the area between curves? then again it's where? It's between the curves, right? So area is where? Area is right here. Yes?
Yes.
So, simple question. Is this formula still valid? F of x minus g of x. Is it still valid?
Yes.
No. Are we still getting positive area?
Yes.
Okay, so let's talk about this. Right, so look, if you, again, think about formula as two separate integrals, integral of f of x and integral of g of x, right? If you think about integral of f of x, that's what you get, right? If you look at the picture, take a look. You'll get just this area right here. Yes, no? But then, if you go to another one, which is g of x, well, you get this area, but this area is what? Negative, yes, no? But since we're putting what? Minus, right? We're putting minus, so what do you have? You have f of x minus, and then negative area. So in that case, you what? Adding them, right? So you're getting all of this. So the formula is still valid. So the top one is positive, right? The bottom one is negative, but we are subtracting, so this negative and negative gives you what? Positive, and you will have this area. So formula is still good. And what do you think the third possibility? Well from the bottom, right? Okay. So that can be interesting, okay, picture. So I'm going to put it like this. So A, B, and let's say we have here y equals f of x, and right here we have y equals g of x. So we're still talking about area between the curves, so area is right here. So the question is, how in the world will it get this area positive if everything sits on the bottom?
Well, no, it's fine because when you subtract the top one is the smaller negative than the bottom one. So when you're adding, well, you're subtracting the bottom one, which is also negative. Since it's bigger, it will become positive.
Good, that's right, absolutely right. So look, if I'm looking just for the integral of f of x, let's say, then you will be talking about area under the curve, right? So this piece. And it's negative, right? And then you're looking for the integral of g of x. It's still negative, but it's negative larger, yes, no, as the size. But then formula is still saying what? Minus. So you will have negative and negative, that gives you what? Positive, so it's still positive. So the formula still works even for this. So no matter what, we're always getting it positive. So this is what I told you, that we have sometimes negative, but sometimes we have always positive. So every time when I have area between the curves, it's always positive, no matter where I have it. So that's the concept, and this is the formula. Again, I want to repeat. It's always the top minus what? The bottom. So please don't forget this. Now, and when I say the top minus the bottom, that means you need to have your calculator handy. Because you want to see the picture. Okay, I'm not saying you have to grasp or sketch the functions manually. No, you just want to see the picture and you want to know what you have for the top, for the bottom. Now, the other thing why you need your calculator, because you also need your upper and lower limits. They will not be given to you, or interval, let's say, for most of the functions. Sometimes you'll get them, specifically when we talk about trig. Okay, because obvious, the functions are fluctuating, right, like sine, cosine. So we need to have interval. But normally we don't get the interval. So let's start with the first problem. So you have function y equals x squared. And the second function is y equals 2x minus x squared. And we need to find area between these two curves. Well, get your calculators. Let's take a look how the picture will be looking. And the main thing I need to know, the one that sits on the top, now this one is easier, okay, but anyway. The one that sits on the top, but also I need my interval, or I need my upper and lower limit. So with x squared, that's not that complicated. So let's say I have x squared over here. This is just a sketch, okay? But then I have 2x minus x squared. So if you go to the calculator and see what you have, so let's put first one x squared, and then we'll put the second one 2x minus x squared, and we graph them. So that's the first one, and there's the second one. Okay, so overall, if I do the sketching, it's going to go like this. All right, so now, and I'll zoom in. I have a picture for you on the paper, but that's okay. So this is what we have. So now, very important question, maybe easy, but still important question. Where is my area? So don't forget, we're talking about what area, not under the curve, right? We're talking about what area, what?
Between.
Between the curves, right? So where's the area? So area is over here. This is the one we're looking at. Okay, so let me switch this. So here's the area that you have to pay attention to. Yes, no? But this can be easy or a very difficult question, and also the answer can be right or wrong just based on your interpretation of that here. So please don't forget, we have to be very careful right here. Okay, so this is my picture. The next question, what do I need? I need my upper and lower limit, right? So the question is, on what interval I have this area? And it will be from 0 to what?
Intersections.
2, 1. Okay? So I actually have everything what I need to set up the integral. Now, overall, let me ask the question. Overall, let's say, do you know how to find these points? What do you have to do? How do you get these points manually, not using your calculator, okay? How do you do this? How do you get points of intersections? Right, you set them equal to each other, okay? And then you will have simple quadratic equation to solve. I don't know if I have to do it, but we can do this, okay? Just to prove what we're talking about. So overall, we'll have 2x squared minus 2x equals 0, right? Manually. You factor out 2x, and you get x minus 1. Zero product property to x equals 0, x equals 1, x equals 0. Well, I already said x equals 1, so that's okay. So this is what you have. Here's your 0, here's your 1, right? So, going to the area, don't forget, it says the top minus the bottom. So which one is the top?
2x minus x squared.
Right, don't flip them. And then you still have to subtract the other one, which is x squared dx. So our integral now is from 0 to 1, 2x minus x squared dx, actually 2x, right? 2x squared dx. Well, now it's a simple integral, and we'll just continue with integration. So, what do we get here? We have x squared, right? And the derivative of 2x is what? 2x squared over 2, right? So 2 will be canceled. And here you'll have 2/3 x to the third. And we have this from 0 to 1. So we have 1 minus 2/3. That's what we get when we substitute 1. And then substitution of 0 just produces 0. So overall we'll have what? 1 over 1 over 3, and that's the area. So question right now. When we were looking before in chapter 5 for the area under the curve, we could use our calculator, right, and find the area. Do you understand that? Right? You could use either the function or you actually graph it and use the other thing that you can find the area. But how do we know? How can we use calculator to check if we did this right here? how can we do this?
You have to do some and subtract.
What do you mean?
The 2 times 12 twice.
So, I mean, remember I said you're using a calculus to check if you're doing right or wrong. So, you still need to find the way out, right? So, overall, you, for example, can find integral of what? The top, right? The whole thing?
Yeah.
Right? And then what?
Subtract the integral of g of x. Yes.
Okay, and then you find the difference, right?
Yeah.
Okay, so that can be done, or basically you only substitute into your calculator this function, right? You see what I'm saying? But what's happening, this is not the original one, right? You're doing some work. And what will be the same, only the answer, but not the picture. So really, when you're working with the area between the curves, and I want you to listen carefully right now, I really don't want you to use graphing. I want you to use the function. Remember I showed you? Let's go back to this. So what I'm talking about, if you're working with the area under the curve, so it really doesn't make any difference. You may see the picture, how it shades and all that, okay? But not to be confused, when you're looking for the area between the curves, don't use the graphing part. What you should do, you should go to math, go down, remember that number 9 that I told you, this function? Okay, we talked about this, I think, right? Maybe, maybe not. I think we did.
We did.
I think we did. So right now, I will put my function in, but just this as a result. Okay, I'll put 2x minus 2x squared. I'll put, now again, my calculus is older, so I have to put this whole thing. Newer calculus actually showed the integral sign, and then upper and lower limits, but here I have to go through this. And my integral will be with x as the variable, and then I'll go from 0 to 1. Okay, so this is my setup. And then I hit enter, and I'll get this, which is what? 1/3. Now, the reason I said that I don't want to see the graph, because here's the thing. If you go back to your graph, this is the area that you're looking for, right? Do you understand that? But the problem is calculator doesn't know how to shade that little thing. Your calculator still only does area under the curve. Do you understand what I'm saying? Only area under the curve. So just going to second trace is not going to help. So what I have to do, I actually have to do all the work that we just did. All of this setup, subtraction, putting this, and I can put this into and treat this as what? Area what? Under the curve. But picture will be different because look, if I put this 2x minus 2x squared, right? That's what we have here. And when you graph it, it's not going to look you're not going to see two functions. Do you understand that? And if you go with the integral, so what you get from 0 to 1, and this is what will be shaded. But what do we have the same? Just the answer. But picture is different. You understand what I'm saying? It's just because calculator doesn't know what area between the curves is. Your calculator only understands area under the curve. So after doing a little manipulation here, fitting this into formula and putting this, you'll get the picture, but this is not your picture. Here's your picture. Okay? Here's your picture. This is what we're looking at. But that picture that you're looking at, the screen seeing calculator, has exactly the same area. Do you understand that? So what I'm saying, put this on your calculator, and then if you're planning to check if you're doing all this work right, use this one, but don't use the graphic part. Just go to the function, put it in, and see what you get. Okay? So let's keep going. Let's do one more easy problem. Then we'll do one more complicated problem. So we have two functions, y equals sine of x. The second one is y equals cosine of x. and the interval that we're working is pi from 0 to pi over 2. Alright, so now you really have to see how this works. Don't forget, your calculus must be in radians, not degrees. Now, I kind of will be guessing right now, okay, overall, but let's say this is 0, and let's say this one is pi over 2. And obvious cosine, when x is 0, cosine is 1, so here's my 1. So cosine, let's say, goes like this. And cosine at pi over 2 is what? 0. Okay, so that's what I have right here, 0. Then I'm going to graph what? Sine, right? So sine at 0 is 0, and at pi over 2 is what? 1, right? So my function, let's say, kind of goes like this. So that will be my sine. And we have it pi over 2, so I can put the line here. Now, we don't have it really, but I'm just putting the limit to my interval. So here's my question. What area do I have to shade, speaking about area between the curves? So again, we're not just, because there's so many pieces here that you can consider as the area, right? But don't forget, we're only looking for the area between the curves, right? So what do we have here? We have this piece, and we have this piece. Do you see the picture? Yes, no? Now, this is a big deal overall, okay? Don't think it's like, who cares? It's a big deal for you to get this right. Because look right now. What do you see different from the previous example? If you look at this piece, for example, what? Cosine is on the top, then what? Sine is on the bottom, right? When you go over here, then what? Sine is on the top, what? Cosine is what? On the bottom, so what that means? It means not one integral, but what? Two integrals. Okay, because you're flipping the functions, okay? And then I need to know what this is, the intersection. Well, you know what that is. Tell me what that is. It's pi over 4, right? That's where sine and cosine have the same values. So, if we're setting up the area, we have integral from 0 to pi over 4, and here we have cosine of x. Don't forget, cosine is on the top of this interval. It's right here. Here's your cosine, minus sine of x dx, and then plus integral from pi over 4 to pi over 2, but this time is what? What do we get?
Sine minus cosine.
Sine of x minus cosine of x dx, right?
That's 1.
So you see now it's getting more challenging because your function is jumping around, okay? But what can you think about this problem? Can you see that those two pieces are the same? Right? So I don't have to work with two integrals. I can only work with what? One. But I can double it. Okay, you understand that? Now this time it has nothing to do with even odd, okay? We're just looking at the pieces of areas and we recognize that they are the same. So I can double it, and if I am smart enough, right, I will not go from pi over 4 to pi over 2. I will go from what? From 0, right? Because I want 0. But the rule is still the same. The top minus the bottom one. You cannot flip the function. So if you're working on this interval, you go from what? Cosine minus what? Sine, right? So there's more than just, well, put the integral. We have two integrals, but we actually can shrink. Now, does it work all the time? Getting the same portions? The answer is no. So sometimes we have to go with two integrals to get the area. Well, that's the setup. So now let's finish quickly. we shouldn't have any problems to find antiderivative here. Alright, so what is the antiderivative for cosine?
Sine.
So this will be sine of x, alright? Then what is the antiderivative for sine?
Negative cosine.
Negative cosine, right? And from 0 to what? Pi over 4, right? Well, I'm going to put one extra line because we know it will be plus. Well, and then just substitute. Now I'm going to take this 2 completely outside, okay? And now what I have sine of pi over 4 plus cosine of pi over 4. That's the substitution of pi over 4 into my function. And then I have minus, and I have sine of 0 minus, plus, cosine of 0, and close the parentheses. Again, by looking at your previous exams, I know some of you are not friends with the parentheses. But it's important to know where to put them. So, what do I get? I get 2, right? Now, what do I get right here? So we know what sine of pi over 4 is. What's that? Square root of 2 over 2, right? Cosine of pi over 4 is the same, right? So square root of 2 plus square root of 2 is what? Square root of 2, right? Minus sine of 0 is what? 0. Cosine of 0 is 1. So you get just minus 1. And this is the exact value. And your calculator cannot change the decimal to this form because we have irrational number. Okay, your calculator cannot do irrational number. Well, that's the answer. So you see the difficulty now increased because we have functions flipped. So I want to make sure I know which one's on the top, which one's on the bottom, and I have to split this into 2 integrals. And the good news was that we had the same pieces, so we could double it. Okay? Now, let's take a look at one more. And this will be the last one. So, overall, 3 problems. Not a lot, but I hope the concept will be clear exactly what we have to do. And please, again, analyze your problems the way you will be doing them on the exam. Not like looking at WebAssign and having 4 choices to choose from. Like the pictures and other things. You really have to graph them. You have to work with your calculator, not with 4 choices, what they give you. Because you don't want to get this wrong just because you don't know how to put this into calculator. So the third one, we have this. Y equals x minus 1. And then the second function we have is y squared equals 2x plus 6. So with some problems, we will have a little difficulty with the graphing. But again, it has nothing to do with the calculus. It's purely 147, 143, 144. So you have to recognize the graphs. So let's just see what we have. So the first one is piece of cake. I have no problem to graph this. It's just a line. So let's say this is negative 1 right here. Slope is 1. So I have a line. Almost straight line. Well, the question is, how do I graph the second curve? And by the way, can you recognize what that is? What is y squared equals 2x plus 6? Now, you all learned conic sections, right? Conics, yes, no? You're surprised, I don't know why. Okay, so, Medicare, conics, did you learn that? Ah, the silence.
Yes, we learned that.
Okay. Well, we're talking about what? Ellipses?
Yeah.
Circles?
Circles.
Hyperbolas? Parabolas,
Parabolas.
right? From different point of view, not just like normal parabola we have. Okay. But anyway. Well, and what do? Well, the easiest way to graph this, remember, your calculator only can handle what y equals, right? So I'm going to take the square root, but don't forget to put plus or minus, right? So we'll have y equals plus or minus square root of 2x plus 6. And now you can put them into your calculator. So what's going to happen, you will not have normal parabola. When we say normal, it's what? Looking up or looking down. You actually have parabola on the side, right? And if you put this, what you're going to see, you're going to see that you have one piece here, negative, one piece what? Positive. And this is what you get when you graph this. This point right here, you can get from your calculator, this will be -3. And then you need to have this point right here and this point, okay? Everything that intersects will help if you can recognize those points. So you can find intersections, okay? That's, I think you can handle this. So this point is -1, -2 right here. And this one will be 5 and 4. All right. Can you see the area? And again, speaking about what? Area between the curves, not under. So area is right here.
-3 to 5. Yeah.
Not this tiny little, looks like almost triangle. No, that has nothing to do with the picture. This is what we're looking at. Now, here's the question. Let's take a look carefully. If we're looking for the area between the curves, if you go from left to right, you go from -3, yes, no?
Yes.
Can you go straight to -5 as one integral? Can you go from this -3 straight to the end, which is 5 over here? Can you go with one integral? And how do you know if you can go with one integral? Okay, you may have this question. Well, do what we're supposed to do. We do what? The top minus what?
Bottom.
The bottom, right? Well, the top is easy. It's only one function. But look at the bottom. What do you see? Do you see that you don't have one function on the bottom? Do you see two functions? And when I say two functions, this is what we have. This is your top. That's no problem here. Where the problem is right here. Why? Because this is one function, and then you have what? The second function. Can you see this? This and this is not one function, okay? And we have two functions. So that means you cannot do this with one integral. You have to split this. So one integral that you will be working with will be this piece. So first you find area of this. Because you cannot do the splitting in two functions. I mean, having two functions on the bottom doesn't work with one integral. So when we go with the area, the first integral that you will have will be from -3 to -1. This is your -1 over here, okay? This is your -1. So you go from -3 to -1. Why? Because you have different function on the bottom. And when you do this, what's the top? What's the equation of the top?
Square root of 2x plus 2.
Square root of 2x plus 6. Good. That formula says minus g of x, right? What's the equation of the bottom one?
-2 radical 2x plus 6.
Right, so it'll be negative square root of 2x plus 6. But don't forget, formula is still saying do minus, right? So this is the integral that describes the area between those two parabolas, pieces of parabolas, if I put it this way. This is the integral that describes this. But then I have to go to plus and deal with the second piece, and the second piece will be from what to what?
-1 to 5.
From -1 to 5, and the rule is still the top, and the top is still your square root, 2x plus 6. And what's the bottom?
X plus 9.
X minus what? 1. It's a line, right? So minus x minus 1 and dx. So as you see, it's getting more complicated if you don't have one curve on the top and one curve on the bottom. Now, technically, it can be backwards. You have two functions on the top and only one function on the bottom. You still have to split. Okay, that's not going to work so easily here. Now, let's quickly reduce this, because what do you get right here? You get this will be plus, yes, no?
Yes.
So you get 2 of them. So 2 square roots, 2x plus 6 dx. So that's this one. And here, the only thing what I can do is just to open parentheses at this moment. So I have square root of 2x plus 6 minus x plus 1 dx. Now, it's not that difficult. It just takes time. Now, if you look at the first integral right here, you can move 2 outside. Right? But then you have to go with what?
Daily announcement. Canned food drive at the Century Cinemas. The canned
Then
food
you have to
will be
go
at
with the
Century Cinemas
substitution.
Saturday,
You
November
said that, yes,
24th, which shows at 9 a.m.
Because you have to
and
say
11
what
a.m.
u is what?
The
2x
movie shows at
plus
Jumanji and
1.
Hotel Transylvania
Six.
3.
I mean, it's a simple substitution, takes time. Okay? So we can do this. When you go to this, you have to go from left to right, so you take care of this. Again, the same substitution.
Please get your orders in
And now this will be easy.
Dinner and options
Now,
coming up
you may
December
say, like, why are you not
1st.
writing what you're
For
doing?
Mr. Bird to sell
Oh,
to your
because
friends,
there's
neighbors,
another way
and
to do it,
supporters.
my
We would
cheese.
love to have a full house.
So from now
Medical will be
on,
hosting an activity known
you will
as
have a
Eye.
choice.
This is an interactive assembly
and I'll
that
explain you what the
works
choice
together.
is in a
It will
moment.
take place
And
under
I need like 2
7
minutes, and
first
tomorrow
3
we'll
hours of
finish,
school.
okay?
You'll
But
be able to attend
uh,
passing all
what I'm
classes.
saying the
If you would
second.
like to attend, sign up in the front office and take up a permission
Well,
slip.
this
Sign
or
up fast.
these
We were
integrals,
only
let's
able
put
to
it
take
this
the
way.
first 126
These integrals
signed.
were done
Magic
with
Valley
the
Philharmonic
idea
Orchestra,
that
Philharmonic
my
Orchestra
x is
performance.
the variable. You understand?
Sign up
That's
for
the one.
team and
X-axis, right?
students, band students, and
But
teachers
if
from the
you
will be
do
performing
this,
with the Magic Philharmonic Orchestra. The concert starts at 7:30 p.m. at
and
the
then
High
look
School.
down,
Tickets are $3 for students, for your fellow students and teachers.
then what do you have on the top?
Don't
One
forget to
function,
fuel your
yes,
body
sir.
for after-school activities.
And what do you have on the
Our
bottom?
station is open Tuesdays and Thursdays after
One
school for healthy snacks. As
So
well
in
as
this
Thursday
case, you
and
will have only
Friday,
one.
remember to take part in Strong in the Champions
One
League.
integral, not one. 2 integrals like I had before. But the difference now, it's not dx anymore. Now it will be what? dy. So you have to decide from now on, when you're talking about areas, are you going to work with dy or dx? And the question, it's not like when you like dx and it's always dx. No, it's what's easier and it's what's better. Okay? The other thing is, when we go to volumes, for volumes, you will not have any choice. It all depends what you have as the axis of rotation. And axis of rotation will dictate if it's dx or dy. So there's this love relationship with dx maybe will be broken. You have to follow that axis of rotation. So keep this in mind. From now on, we have to decide what really we'll have if we have dx and dy. Here, for the area, I can choose. For volume, you cannot choose. Okay? You have to follow the process. And here I have to decide. And obviously, it will be much easier if I go with what? dy. So I'm going to stop right now. So tomorrow we'll come back to this problem, okay? And I will finish this problem, but again with dy. I'm not going to do dx, okay? I don't like it. I'm just showing how we go and how we can get into a little trouble if we decided to follow this one way. So tomorrow we'll finish this. And we'll start volumes. And please, again, don't put this aside. At least pick up a couple problems that you will still remember what just happened today. All right, so I'll see you tomorrow.
Thank you.
Welcome. Okay, I put this paper back.
Oh, I will not be here tomorrow. I need to get you the doodah.
The doodah.